Hey, College Math, welcome back. Here is 6.3, where we talk about Euler paths and circuits. Okay, so our objectives are to define and find Euler paths and circuits in connected graphs. I can't remember if this is the first time we talked about it in this class, but this word right here is pronounced Euler. It's the last name of a really famous mathematician who founded a lot of stuff in math. If you decide to go further on in math and take a few more math classes after you graduate in college or in university, you're gonna see his name pop up quite a bit. So don't be surprised if you see it in other kind of math subjects, right? But it is pronounced Euler. Um, yeah. So just a little review from 6.1. So a path, it's a sequence of vertices and edges without repeating an edge, right? And then a circuit is a path that starts and ends at the same vertex. All right. Since we're going to be talking about a specific kind of path and circuit, let's just kind of, go back and redefine those. And then now the new paths and circuits we're talking about are Euler paths and Euler circuits. So what's the point of those, or what's the significance? Well, an Euler path is a path that travels through every edge of a connected graph exactly once. So we're walking along the edges and the vertices, and we're only gonna visit every edge once. So I can't go back to an edge that I've already used. And then in an Euler circuit, it's an Euler path that starts and ends at the same vertex. Okay. And then, sorry, one last thing about the Euler path. Not only are you not visiting an edge more than once, you're using every single edge, right? In an Euler path, or in just a path, I don't need to use every single edge, but in an Euler path, I have to use every single one. That's kind of the idea behind it, okay? So let's go ahead and just find a couple. It's a lot easier to visualize once we try to find some, okay? So find an Euler path in the graph below. So we can pretty much start at any edge or at any vertex or edge that we want. No, sorry, let me rewind. We can start at whatever vertex we want, right? As long as we're gonna cover every single edge exactly once, right? So maybe let's go ahead and just start at F. There's our starting point, okay? And the way I'm gonna write my Euler path down is I'm gonna list out the vertices in the order that I visited them, okay? So I'll start with F, okay? And from F, let's say I go to A. Right, and it's going to help you a lot if you redraw the graph, and then as you're kind of visiting the vertices and going through the edges, kind of put a little mark or scribble out the edge you already used so that you know that you've already visited that edge and you don't want to go there again, right? So I've already kind of went through this edge to get to A. From A, I can go to B. From B, I can go to C. Okay, and then from C, I can go back to F. It's okay if I go back to the same vertex as long as I don't end there, okay? So I'm not ending at F, which means that's okay. And then from F, I'm going to go to E. From E, I am going to go to C. Okay, look, I'm back at C, and that's okay because I'm not touching an edge that I've already visited. From C, I'm going to D. And then from D, I'm going to go to E. Okay, and I can look back, and if you see, I've visited every single edge, I've touched every single one of them, I've crossed them exactly once, and I ended at a different vertex than I started. I ended at E. And so there's an Euler path, there's an example, okay? You can actually find multiple Euler paths in this one graph. Here's another example. E, C, D, E, F, C, B, A, and then F. Here's another example of an Euler path. If you, it's a little bit cheating, it's a little bit backwards of this one, but it's completely different because I'm starting at a different circuit than I'm ending with compared to that one, right? So you can find lots of different paths. The kind of trick is to always start at an odd vertex, okay? And what I mean by odd is a vertex with odd degree, okay? So for a path, not just any path, but an Euler path. I'll do it in a different color, Euler path. start at a vertex with odd degree. Okay, so now let's go ahead and try finding an Euler circuit in a different graph. Okay, so here's another graph. We'll find an Euler circuit here. All right, so now let's go ahead and try that. We're gonna go ahead, I'm gonna start at F. Okay, why not, right? So F, and I think I think I started an F in the last one, yeah. Okay, we'll start an F in this one as well. I can go from F to H. Okay, remember the goal here for an Euler circuit is to end at F, okay? So I'm gonna visit every single edge and I wanna make F the last vertex that I hit, okay? So I can go from H to G. I have really no other option, right? So H to G, and then G back to F. Remember, that's okay. And then from F, I can go to D. From D, I can go to E. Okay, from E to C. From C to D. Okay, so I'm gonna go back to D, and then again, that's okay. From D, I'm gonna go to A. And then from A, I'm gonna go to B. From B down to E. And then from E back home to F. Okay, and then review your graph. Did I hit every single one of these edges? Yes. And not only did I start at F, I also ended at F. So here's one circuit. Okay, and just like with the other one, in example one, I can find another one. Okay, and you can actually, if you would like to, you can pick another vertex to start at. Maybe start at D, maybe start at A, whatever vertex you'd like to start at. Pick another one and maybe try finding another circuit, okay? With Euler circuits, it's always best to try to start with one that has a lot of edges, because then you know you have multiple opportunities to come back to the end. It's not impossible, but it might be a little bit harder to start at something like A, because if I look at A, there's only 2 edges coming out of it. So I have to be careful. I can only come back, I can only leave A once and then come back to it once, right? I'll only be able to visit it twice in this case because there's 2 edges coming out of it. So that means I have to visit every single other edge before I can come back to this one, okay? So it might be a little bit harder. It's probably possible. I'm not sure. You can't always immediately tell if there's a circuit starting at a specific vertex, but it's always kind of worth a shot, okay? With paths and circuits, there's never like oops, I just zoomed in quite a bit. There we go. There's never a surefire way to tell, okay, that's going to be the circuit. A lot of the times it might be a little bit of trial and error. Like you might be going through and like, oh crap, I visited an edge twice. You might have to go back and start over or kind of erase a little bit of your progress. Okay, so easiest way to find one is just to jump right in, pick a vertex and go and see if you can kind of get it on the first try. It might take you a little bit, okay? Not a whole lot though. All right, so now kind of another thing to say, okay, if the question isn't necessarily what is the Euler circuit or the Euler path when I look at a graph, but the question might be, how do I know that this has an Euler circuit or a path? How do I know that I'm not wasting my time in a graph that doesn't even have an Euler path or an Euler circuit, right? Because there are graphs that don't have either. And so let's go ahead and try to figure out, or let's go ahead and see what we can do to help us in terms of looking for a graph that actually does have an Euler path or circuit, right? So how do we know if a graph has an Euler path or circuit? Well, here are 2 different things you can look for, okay? A graph has an Euler path, oops, if 2 or less of its vertices have odd degree, and then a graph has an Euler circuit if every vertex has even degree. Okay, and then a couple, like 2 extra notes I can write here. So one note is that has to be connected graph, right? Has to be a connected. If I can spell connected, there we go. Has to be a connected graph. Okay, if the graph isn't connected, there's no point in even looking for a path or a circuit, right? And then for an Euler circuit, if the graph has an Euler circuit, it has an Euler path. Okay, that's just an immediate, that's true because, why is that true? A graph has an Euler path if two or less of its vertices have odd degree. Well, if it's an Euler circuit, or sorry, if it's an Euler circuit, it has all vertices that are an even degree. And so that means that two or less have an odd degree, because in this case, none of them have an odd degree, and that 0 vertices with odd degree is less than 2, right? So it immediately will have an Euler path. Okay, and so we can kind of use that information to find or to see in these graphs if they have a path or a circuit or both, right? So that's our last example. Tell whether the following graphs have an Euler path or circuit or both, right? And then explain why briefly. So if I look at this first one, okay, the idea is pretty much that you're just counting the degrees of each vertex. So I'm going to go ahead and mark them at each vertex. This vertex at the top has a degree of 2. This one right here has 1, 2, 3, 4. This one has 1, 2, 1, 2, 3, 4, 2, and then 4. So this one has an Euler circuit. Okay, and why? Because every single degree is even. Or all vertices have even degree. Have even degree. Okay, and I'm actually going to modify the instructions here a little bit. We're not going to worry about the both case because it'll get a little bit redundant. I'm kind of more concerned with the path or the circuit. We'll just kind of assume, okay, if we say that it has a circuit, then yeah, it'll have a path. Okay, but that's kind of boring. So just worry about path or circuit based off of the two rules. Okay, so that one has a circuit, technically also a path, but whatever, right? Now let's look at B. Let's see all our vertices. I have one here that's 3. Okay, I already have an odd one to begin with. Here's 3. Okay, kind of walk in the line here, and this one also has 3. So now this no longer has anything. So this has neither. Okay, and so I guess here I should have put or neither. Okay, because we do have a case where it's neither. All right, and so if it breaks the path one, then it definitely can't have a circuit either, right? Because everything has to have even degree. So the second I found the first vertex had odd degree, definitely not a circuit. Still has a chance to be a path, but because now I have more than 2 vertices that have odd degree, definitely not a path either. Okay, now the last one over here, let's go ahead and write down our degrees. I have 2, 3, okay, a little dangerous there. This one has 4. This one has 1, 2, 3, 4, and this one has 1. Okay, so I have exactly 2 that are odd, and so this one has an Euler path. Okay, and so 2 vertices with odd degree. Okay, and there we go. Pretty not terrible, right? Just kind of looking at all the vertices and counting up the degree, how many edges are coming out or into that vertex, and kind of using these 2 rules to help you a little, okay? So actually I'm gonna make a little bit of an edit. We're just not gonna worry about this one. Okay, that just seems kind of redundant. We'll just not regard that at all. We'll go ahead and just worry about, okay, if it's a circuit, it might have a path, but we don't really care because it has a circuit. And then path, just because there's a path, probably does not mean that it will have a circuit, right? It does not directly lead to that. All right, that is 6.3. Hopefully that sounds good to you. I will see you in the next one. Bye-bye.